All right, good morning. Here we are, April 15. I suppose many of you are done with programming assignment 3, right? But you have a few hours depending on when your section is. I'll have office hours after this, and you could come and ask if you have any last-minute questions. But that's basically what's going to happen. I will talk today a little bit about program assignment 4. I will just finish up reviewing what we did last week, so finishing up 5, talking a little bit about program assignment 4, which is all about chapter 5. There is no program assignment on chapter 6. And then we'll start with chapter 6, and then we're done forever. So that's the plan. What is it? Yeah, it's basically just 2 weeks. But I have a lot of reviews, so I'll run behind and stuff. The reason I do it like this is that I really want to ask homework questions on this that is due on the last week, right? Although I was told that you're allowed to have homework due on the triple R week. Maybe that's the plan for the future. Because here we lose a whole week almost in terms of actual homework material. But for now, I'll stick to this, of course. And for the future, you all know that Wednesday, May 14th is marked for the final exam. Chapter 5, finishing it up. We did, there are so many things here, and I know it might be confusing. The last things we did, going back actually to the Tuesday from them before, is that we tried to talk about something called zero stability, or stability for multi-step methods. So just some terminology reviewing here. You want something called convergence. I say that word all the time. Convergence is great. It means that your true solution, y, or your numerical solution, w's, approaches the true solution, y, at each time step. And there's a max here saying the worst possible error goes to 0 as h goes to 0. That's really what you want of these methods. If you do Euler and it doesn't look good enough, you bring down h and it gets closer, right? And you know already, our proof, remember we have an error bound for Euler? The very fact that it was h times something means that it's convergent, right? It comes straight forward from that. If you have an error bound saying that the error is h times something, clearly it goes to 0 as h goes to 0. But if we go a little slower, so the goal of this chapter is to try to show the same thing for other methods. Let's see, for one-step method, we can define a consistent trication error to say that tau goes to 0. That's not at all as strong, because it means that that's just a one step. Remember, we had taus that were h squared divided by 8. For Euler, we got a tau that was h half, I think. When did we first start talking about taus? Going too fast, going too fast. There's our local truncation. Maybe I didn't do it. Yeah, but when we did this proof, we didn't really call it tau. But then we introduced tau, and I guess we never wrote it out explicitly. Okay, fine, but it's h half something. So tau being going to 0 is, of course, you can easily convince yourself that that's a necessary condition for having convergence, which is the ultimate thing. But the interesting thing here is that it's not quite enough, especially not for multi-step methods. But the big thing is that for one-step method, it is enough. So if you take one step and the error gets smaller and smaller as h shrinks, then you have convergence. And that's what this big theorem is saying. So one-step methods are kind of just a question of studying tau. And this is, if you remember what we did back in Runge-Kutta, it was all about tau. I didn't even talk about something called stability because there was no issue. But here's the theorem justifying that. That basically it's saying that you can write any method, you replace this f by a phi, which is, turns out, all these Runge-Kuttas, you can do that if they are one step. And it ends up being convergent if and only if it is consistent. You have an error bound very similar to the Euler method, remember? It's just that tau is something else, hopefully higher, because remember, Euler is not a good method, it's just h, right? So hopefully with RK4, there will be an h4 times something there. And then the L is actually a slightly different L, but it's not a big deal. But I did an example on the blackboard where I said that when you do the midpoint method, this L is combined in a nested way. But it's not that important. The important thing is that it really works if you just show. So a typical question here is RK4 convergent? The method you've been using all the time for pendulums and everything. Is it convergent? Can we prove it? Well, we're not proving the theorem, but using this theorem, all you have to show is that it's Lipschitz. That's kind of obvious. You don't have to go through the exercise I did on the blackboard. It's just a bunch of nested f's calling each other, right? So it's certainly Lipschitz. Well, is tau small? Well, that's the difficult part. We didn't do that for RK4, but you can turn the crank and just get all these Taylors out for that one as well. And then you're done. You have a convergent method. Multi-step is much worse. I showed a little nice example of the simplest multi-step method in the world, and it had a small tau, and yet it blew up. So it's not enough But it turns out it's a simple little thing we can add. We need to look at just the A coefficients. Remember, multi-step method has a bunch of A's multiplying the W's and a bunch of B's multiplying F's. And you take all the A's, and the B's are not the issue for this instability. It's how these A's, how these W's combine. It's a recursion equation. And you solve a recursion equation, and you make sure that there are no modes here, or no fundamental solutions with a root that is greater than 1. So any recursion, remember in 10b we're doing Fibonacci, for example. Fibonacci, it's a recursion. It just tells you that if you start with 1, 1, and then you add the two last ones, an is equal to an minus 1 plus an minus 2. That's a recursion, right? Would that one be stable for this method? It's not. It turns out it grows at a rate faster than 1. So you find the roots of this characteristic polynomial, and from the point of view of these methods, it's important that these are less than 1, otherwise it blows up. My little silly problem had two roots, 2 and 1, and that explained why it blew up. When you have that, you have everything you need. So let's see, what are we calling it? The theorem is what I'm looking for. A multi-step method of the form we're looking at is stable if and only if it satisfies the root condition. Okay? And if it also consists, stability is not what we need directly, but it's a famous theorem, the Lax equivalent theorem, saying that consistency plus stability is equivalent to convergence. So that's what this theorem is saying, basically. So how do you check? So if I ask, can you prove that Adams-Bashforth is convergent? To do it, you get to derive a small tau, and that's easy. That's Taylor. We've done it before. And in fact, these Adams-Bashforth, what did we say about them? I'm sure we said that they had small taus. We looked at a few of them. Here's, for example, one Adams-Bashforth. I think I just mentioned in a note that the truncation error scale, like, mixing up, because I teach this in the grad course too. Then I have a big table of all the taus. Anyway, we did a few multi-step methods. In particular, if you take, for example, this guy here, the one we played around with a lot, you can show that it has a fourth order truncation error. So a tau is equal to order H4, and is that enough? No. You have not proven that it's converted. It could be wrong. You've got to also look at the A coefficients, which are very easy for all the Adams methods, because it's really just the first A there is 1, and the first on the right-hand side is 1, and there are no other ones. And I did this example, and the characteristic polynomial for this one was lambda to the n minus lambda to the n minus 1 equals 0. Okay? It's a little, you have to think a little bit about how to get that through, but any method of the form wi plus 1 equals wi plus, and then all the rest doesn't matter, right? Because that's not what comes into play at all. But what does matter is the order of the method, and we do go down all the way to ti minus 3, which means that the characteristic polynomial here is 1 times lambda to the, and if you want to, you could just use the definition here, but you can also think about it, m, the number of steps of the methods. So you end up getting, in this case, it was a 4-step method, and you're getting a 4 there. Then you have minus that coefficient, which is 1 times that guy, and there are no other ones. So this has to be 0. And when is it 0? At 0 and at 1, right? The 1 here is scary because that's really just on the boundary. But if it's not multiple, it's fine. Okay? So there we go. This method, all the balance methods of this form, they satisfy the root condition. Therefore, if you have a tau that is order h or higher, it's going to be convergent. That's how we use this. So the theorem really says that for a multi-step method, you get to check tau, and you get to check the root condition. And I could, of course, make up some other method. In particular, the method I made up that was not good had some weird combination of wi minus 1 coming up here. That was not cool. So anyway, that was the stability. So it is confusing because it's called stability, and now in chapter 5.11, we talk about another type of stability. And I know it's confusing. It's just to keep it strict for this course, this is stability. Sometimes it's emphasized that it's 0 stability because it's as h goes to 0, but just call it stability. And we'll refer to the other one as absolute stability all the time. But this is how you check if a method is working. You'll see, by the way, many people ask how we're studying for the final, etc. We'll show you a lot of old, we often have a problem like this on the finals. I'll show you the one I did last time. You'll see a typical question, or exactly, here's a scheme. Is it convergent? It's really a typical question. And you do some Taylor, and you do some root conditions. Maybe you don't do root conditions. If it's a one-step method, you don't, right? So, you need to just check some understanding and that you know the procedure. So practicing old exams will be good in that sense. But of course, most of these problems can be seen in the homework as well. And you do have homework testing these things. But I think people think that some of the homework problems are just calculator-based. And as I said, of course, they don't show up on the final exam with those weird numbers, right? So running 10 steps of RK4 is just not something you will do in a final exam, even if the numbers are trivial. Yeah. So I'll ask somewhat different question. But I would definitely ask, why don't you take 1 or 2 steps with RK4 and choose the simplest numbers I can invent? And did someone ask on Piazza whether you need to memorize these coefficients? Not really. If you remember the last exam, I even gave you the error formula for Hermite and everything. I don't want you to memorize, but I'm not telling you either that you absolutely don't have to know it, because what if I ask you to derive the midpoint method? That's fairly easy to do if I tell you how to do it, and you do the steps. But if you remember the formula, that would help you, right? So study with some common sense. But this course is not so much about memorization, for sure. More about understanding. Anyway, let's do this 511 thing, which is the last key part of understanding these methods. And it addresses an issue called stiff equations. And what is a stiff differential equation? It's hard to define. I think this is almost the best definition. It's numerically unstable unless the step size is extremely small or much smaller than you want. And it's very iffy. It's a very non-mathematical definition. But it's really what it's all about. If you can run many of the problems we run, your pendulum is not stiff. Why? Because you're not suffering. I don't know if you know it. Maybe your 1,000 steps. Was it 2,000? Yeah. The steps you took, maybe that's way too much, but it's not. It's just a reasonable number of steps you're taking, and you're not suffering. Suppose that you ran your pendulum and it just blew up. And it was not because your F pen was wrong, but because the numerics was such that it blew up. And then you bring down h, and finally, when you have 10 to the minus 9 or something insane, you have to take 1 billion steps, and then it works. That would be a stiff equation. You're taking an h that is much smaller than is reasonable for your problem. But it's always going to be this vague, so it depends on what's unreasonable. But a test problem would be this. I did y prime equals minus y, but it's all scaling with this lambda, so this number here. So let's do something minus 30. And you know the true solution is really dying off extremely fast. And the way to understand this is to say you're not scaling time. You're living on a time scale that is order 1. So other things are happening in this equation on a normal time scale. But then you have this guy dying out almost immediately, right? Or set 30 to 3 million if you want, whatever. It dies out very quickly, okay? It's true that that 30 will dictate the time step you can take with, for example, RK4. And in fact, you can try this out. I didn't do it, but with Euler, we could see already at 0.1, RK4 blows up. So 0.1 would be a reasonable time step if there are other things happening on the scale of order of seconds, right? But it will blow up because of that annoying term. That's a stiff equation. Turns out you get a switch method. Backward Euler would work great because it has better stability property. So let's analyze this. Analyzing it is quite easy. We always look at just the test equation. That's actually enough to look at a number of stiff problems. We'll just look at the simplest test equation. So as soon as I talk about absolute stability or stability regions, the test equation here is what we're talking about. It's just a linear scalar equation lambda. And almost any, well, the true solution is, of course, e to the lambda t. And almost any method, let's say Euler's, you can just plug this in and get an explicit expression for wj plus 1. In this case, you take a number here, which is 1 plus h lambda. Remember, it scales with the step size and how fast your equation is, the lambda coefficient, to the power of j plus 1. And already here, you can kind of tell that since you know, if you know that the true solution is damping. So in practice, we're actually mostly interested in lambdas that are negative. Otherwise, you would be modeling an explosion, which is fine. But then you want the numerical solution to blow up. So then this is a different issue. The most common scenario, most things in nature are decaying or staying where they are. And then you don't want the numerical methods to blow up. And it's clear from this immediately that 1 plus h lambda cannot be greater than 1. That's how simple it ends up being for Euler. You can write it out, but that's what it ends up being. 1 plus h lambda cannot be greater than 1. So that was easy, and that actually gave us a condition. Remember, I'm putting absolute values here because the lambdas are going to be imaginary. And the reason is, for very simple things such as your pendulum, you know from Math 54 that the way you solve systems of equations is to diagonalize. And even if you have real numbers, like in your pendulum, you get the imaginary eigenvalues out. So that's a process. We don't go through it completely, but for now, just understand that we want to solve this test equation, and these lambdas can certainly be complex. And then it's important to put an absolute value there. And what can we say about this condition? So far, I haven't really made an absolute. When I solved for it like this, I kind of assumed that it was real. But if we look at, if we look at the complex case, I mentioned that it's really just a circle centered at -1 that looks like that, and it's only stable inside that circle. Okay? In other words, 1 plus an h lambda inside this circle has a magnitude less than 1. And that you can verify. It's just complex. It's just thinking about what it means. That's good. So your h lambda has to be in here. What if I ask you to solve this equation with -30? Well, -30 is over here, right? It tells you that you must multiply by h equals, so it ends up at 2. 2 divided by 30. Okay, 1/15. Then it works for Euler. Okay? What if I ask you to solve a pendulum problem where you're solving lambda equals I here, or I anywhere, 30I instead? That's an equation that is oscillatory. It's very interesting to solve. Any type of thing oscillating would have a 30I eigenvalue, or lambda there. Well, you can't multiply it by anything and get inside this region. So Euler's method is always unstable for purely oscillatory system. So clearly Euler is not enough. We're not too happy with Euler, but sometimes it works. If you have a mixture, if you have here, you would have let's say a spring that is damped, so it decays like this, then you know that you will get eigenvalues that are both a combination of e to the minus something and sine and cos, right? And then, indeed, you can multiply by an h, so you end up inside here. So Euler might work. That's the setting. Anyway, then we keep on going and look at other methods, and it's actually very easy. As easy as this derivation was, to just plug in the test equation, you can do, for example, RK4, and get a big stability region out of that. I'm not doing it here. Did we do the midpoint method? I think we did midpoint, where we just plugged in and got that the stability region was just the same, 1 plus h lambda, but one more term, plus h lambda square half. Okay? And if you do RK4 and keep on calculating. But all these nested f's are easy because it's just linear. It's an easy test equation. So you can plot all of these. And I did have a little script that I called RK4 stability, where we tried a few different ones. But at the end, we ended up plotting the RK4 stability region. And we can see why it's a very popular method and why I asked you to use for the pendulum. It covers, if the inside there is stable, it does cover a little bit of the imaginary axis. So if you ask me to solve a purely oscillatory system, it's going to be stable and nice if you just multiply by a small enough h. Now, you always get a restriction on h. So RK4, as good as it is, it will never be amazing for stiff equations where this h is unreasonably small. But at least it handles the case with the imaginary axis well. So these stability regions tell you a lot. So finally, we went through and said, what if you have these extremely fast processes, these stiff equations? So you have a -30 over here, and you really just don't feel like multiplying by h, to bring it inside the circle. Well, you need a method with a different stability region. And one typical one is, of course, backward Euler that we talked about. Backward Euler, which says Wi plus 1 equals Wi plus h times f of ti plus 1 comma Wi plus 1. Exactly like forward Euler, but replacing this by ti plus 1 instead of I. And it causes a lot of trouble because you can't really use it. You have to solve. You can't just apply it, right? But let me tell you what's good about it. If you set f is equal to lambda y here, then you get Wi plus 1 equals Wi plus h times lambda Wi plus 1. Right? So you just plug in the test equation in almost anything, and you can easily solve for Wi plus 1, which in this case gives you Wi plus 1 equals 1 over 1 minus h lambda Wi, okay? So just like it's a little more difficult for you guys to solve, but just like before, I can solve Euler's equation. Is that good? Is that a better method? Well, it is a method. You can implement it. You can try it. It looks almost as crappy as forward Euler in terms of accuracy, but it can be improved. But in terms of stability, when is this number less than 1? Well, it turns out it's usually less than 1. For very large h's, that's a huge thing in the denominator, and it's going to be very small, right? And you can make a very similar argument to before to see that backward Euler, that thing there is actually a circle. A circle again, centered at 1 with radius 1 instead of -1. But this time it's stable outside because it's 1 over. So it's stable everywhere except in that circle. Which means that if you solve the -30 thing here, you can just take h equal 1 and you'll be fine. You won't get accuracy, but at least it doesn't blow up. You can certainly do the pendulum. It's just that it's going to damp it out a lot. It's not an accurate method, but it's not unstable. That's the whole moral of that, of this absolute stability. Let me define this region that I'm drawing here. It's called the region of absolute stability, and it's defined to be a number q. So we write all the equations on this form, where wi plus 1 equals to some function of h lambda times wi. And this is what we call q. That's for one-step methods. And it's emphasized, I think, well, I defined it for multi-step, but not for one-step. It's in the book. So that q here that we derived is equal to q. And you look at the area, you look at the places where it's less than 1 in magnitude. That's it. That's the regional absolute stability. And it tells you a lot about which method. A typical question here would, of course, be, here's a method, find its absolute stability region. What is a nice follow-up question? It's like I said, suppose you want to solve a problem with lambda equals I. What is the smallest h you can multiply by to make it stable? And the answer here would be none, because it's going to be greater than 1 no matter what. While here it would say you can choose whatever h you want, and it's not going to blow up. So let me just say how it changes from multi-step, and then we'll go to the programming assignment where I'm asking you to do this. Multi-step's a little bit more complicated, but in a way it's kind of exactly the same. You just plug in the test equation lambda y to this, and you get some expression. The problem is that you have all these w's all over the place. So in order to just figure out what this q is, you get to solve this characteristic polynomial again. Okay? Multi-steps are just weird because they use a lot of older solutions. So it's harder to apply, but you can really just use the characteristic polynomial and at least write up a condition that you can solve with a computer for absolute stability. And doing this, you could, in the grad course, we go through Bad and Bash Force and all of these. We look at regions. They're all interesting in various ways, and there are a lot of interesting methods. But evaluating it is a little difficult. You need to solve characteristic polynomials all over the place to evaluate it. This was so easy. We just plug it in. So, you know, another benefit with one step, at least when it comes to analysis. But this definition generalizes and just said that all these roots coming out of the multi-step must be less than 1 as well. And finally, a definition. A-stability means that everything in the left-hand plane makes it stable. Namely, the numerical scheme will not blow up for it. So if this entire region here includes the left-hand plane, we call it an A-stable method. And you can observe that forward Euler is not A-stable because it's not stable here or here or here or here or here. RK4 was not. Midpoint is not. None of those atoms are. This one are, and it's a very interesting field to study better methods that are A-stable. Why do you want A-stability? Because as I said, that would be kind of the ultimate method, right? Because as I said, suppose you're not studying explosions. Then you're somewhere here. In nature likes to be here somewhere. Some little damp, little oscillatory something, right? These are methods that don't put any numerical stability restrictions on your time step for wherever you are. Sometimes it's a little too much to ask for, but it can be reasonable. What is the price you pay for that? I mean, one thing here is that this is inaccurate, but that's not really the issue. The issue is this. Because this was easy to do for the test problem, but if you want to use this method for a real problem, you have this f of wi plus 1 issue. Think about what this would mean for your pendulum. It's not fun. Because at every step, I would ask you for wi plus 1 equals wi, such that, and here's your big equation with cos and sines and stuff all over the place. How would you solve it? Newton's method. So that leads me to programming assignment 4. Let me say a few words, but since nobody has started, I will just briefly go through it now, and then we'll come back and talk more about it later. Didn't I download it? Yeah, there it is. So what I'm asking you to do is to study this method, backward Euler. It's here. And the first is just pen and paper, writing down how to do exactly what I just said. Suppose you want to solve this. You want to take a step. It's like the thing that was so easy with RK4, you want to take it, it's not going to be easy now. And you're going to describe a Newton's method for doing it. And in a way, it's exactly the same as we did back in chapter 2. It's really just a question of keeping the notation straight. And you know, it's not hard, but the notation makes it confusing. That's known. You're standing at wi, just like before. You know it. H is known. The only thing you don't know is wi plus 1. This is your x, right? You got to write a Newton's method in terms of pretending that's an x. And it's fairly straightforward. And then you implement it, and you test it, and eventually I have a problem where I ask you to run something that can be quite stiff. There's a simple equation, simple model problem that can be really stiff, And you're going to study exactly the things I said, that with this method, you can take whatever step size you want, and it works fine. And then you run it with RK4, and you see that you need a lot of time steps. So that's the pedagogical part here. But I'll come back to the details. I just want to let you know approximately what it's all about. So this will be due in 2 weeks. All right? Any questions on ODs, chapter 5, or anything? Yes? To be equal to 4 here? Yeah. Because I was studying a method, AB4, that went down to something of WI minus 3. So this is what we call a 4-step method, because it uses 1, minus 1, minus 2, minus 3. It uses 4 steps to produce a new value, right? So Euler is a 1-step method. RK4 is as well. If you do Wi plus I minus 1 as well here, it becomes a 2-step, 3-step, and 4-step method. So yeah, this was really just because I decided to look at AB4, Adams-Bashforth force. That's a good question. Although this conclusion doesn't matter because that third didn't matter. So the general conclusion is no matter how high order Adams-Bashforth you're doing, it's going to be stable. I just picked 4 to get the 4 and the 3 there. But yeah, I didn't write that out clearly. More thoughts? This is a huge topic. You can tell from our grad courses, maybe I mentioned that before, that everything we're doing in this class is considered undergrad material in the terms of quadrature, solving equations. All of these things are undergrad material. It's taught in 128A and B. But in the grad courses and the research on these fields are a lot about differential equations. Okay? In fact, we have 3 grad courses on numerics, 228A and 228B, and they're both about differential equations. And we have one which is about chapter 6, linear algebra, or numerical linear algebra. But that shows a little bit how the priorities are here. People want to solve differential equations because they do it in the real world. Of course, in the grad course, we also teach the partial differential equations, PDEs. This is just ODs, but it's kind of the same thing. Anyway, yeah. It's not stable in the right-hand plane? You mean that it's not including these points? The right-hand plane is a very special thing. Because, as I said, if you're here, if you have a lambda here, that means that your equation wants to blow up. And then you're asking, is the equation blowing up? And Euler is saying, yeah, the equation is also blowing up. That may or may not be what it's reasonable. In fact, backward Euler, here's what's not reasonable. Suppose you have an eigenvalue. Suppose you want to solve an explosion. Just the simplest problem in the world. Y prime equals, let's say, 3y. Okay? True solution e to the 3t. This is an explosion. And you're trying to step with h is equal to 1 because you're thinking, why not? Let's just step here, right? That means that you're standing here. 3. Okay? Guess what? This is in the stability region of backward Euler. Which means that, just by the definition, it will decay. So the true solution, y, looks like that. But your numerical method will do that. So backward Euler, that's really bad for backward Euler. It's so extremely stable that it even takes something that is supposed to blow up and makes it decay. And that's not good, of course. But that's not the issue. The issue is that the whole concept of absolute stability region only makes sense if you're in the left-hand plane. And it can be generalized for right-hand plane. But don't worry about explosions for now. So forward Euler is better in that sense. It would better capture what you want, namely that things are increasing, right? It's a little iffy. I agree. But the very basis of this concept is to say, make sure solutions are decaying. That's why we're doing this. We're finding the points where these numbers are less than 1. We want the solutions to decay. That doesn't make sense if you want them to not decay, right? So it's mostly in the left-hand plane. All right, I'm ready for some linear algebra. So here's this funny thing that I think you've been taught forever. We teach it. I mean, we assume you know it when you come in, because the first year, Gaussian elimination, you learn at high school, at least for 3x3s, I'm sure. And then we ask you to use it when you solve for example, coefficients in partial fractions in Math 1b. We ask that you just know it. Then we teach it in Math 54. Then we teach it in Math 110. And now I'm going to teach it here. So, I guess it's an important method, but it's also, maybe people should review. Everybody wants to teach this stuff. It is important. It's done all over the place. This is what supercomputers and small computers, they solve systems a lot. But yeah, I'm going to assume that this is review for you. Let's look at chapter 6 overall. What is it going to be about? First, a really just review, except maybe something called operation count, which I will emphasize a little bit more. Here's more numeric. So we'll emphasize, compared to 110 and all these other courses, we'll emphasize what changes in a computer. Here's just some theory. That really, if you took 110, I know some of you have and some have not, this would be really review, and this would be 2, and this would be a little bit more numerical, maybe. But, much of this chapter is review. We'll try to focus on what changes in a computer. Having said that, of course, we learn all this fancy linear algebra in 110. In the real world, you have these million by million equations that you want to solve. How it works on a computer is kind of critical. So these extensions are very important. Let's get started by just saying the following. We want to solve a linear system. This is the definition of the problem. You have n by n. We assume it's square for now. So you have n equations and n unknowns. And we can write it in this form. And then, of course, you have right-hand sides that are b1 to bn. And we will very soon, at least on the blackboard, I will start writing this as a big matrix A, that is n by n with all those numbers, multiplying your solution vector x, which is a vector with n numbers, and that's supposed to be equal to your right-hand side vector, which is n numbers b. Okay? Just a definition, Gaussian elimination is something called a direct method. And I don't think you've seen any other methods, so it's fine. What they do is that Gaussian elimination, you do a procedure, and when you're done, you're done. It sounds stupid, but that's not true for all methods. There's something called iterative methods that we teach already in 128b, where you have to keep on iterating until it's good enough. This is a different character. A little bit like Newton's method, you have to decide how far to go. Gaussian elimination or direct method do not have that issue. You do a procedure, and when you're done, you have the answer. What is Gaussian elimination based on? It's based on the idea that you have 3 elementary row operations that does not change the solution to the system. Namely, that you can multiply any equation by a lambda and it will still be satisfied. That lambda should not be 0 because then you kill the equation. You can add any equation to any other equation, clearly, because you're just looking for left-hand side equal right-hand side. So if you have 2 equations, adding is fine. And in this case, we go right at it and say you can add a multiple of another equation, where the multiple is non-zero, to any other. Finally, this is something that, again, you might not, well, you've probably seen it. You can switch equations. And when you write it by hand, it's such an obvious thing to do, right? Of course, nobody cares about the order of your equations. In a computer, it's a more explicit thing. So, wow, you need the capability to switch equations. And here's where numerics will make a big difference from hand calculations. And I'll show you why. You've got to switch equations much more often numerically than you do when you do hand calculations. What is the method? Gaussian elimination with backward substitution. It takes a linear system and it reduces to triangular form, typically upper triangular. So it puts zeros below. Using these 3 row operations, it puts 3 zeros below the diagonal, and it's just using these operations. And the triangular form is then solved using backward substitution, where you start at the bottom and go up. And we'll go through this, so I'm just saying this is what the method is. Quickly about the row exchanges, I think you've been taught that if you get a 0 on the diagonal where you're standing, the so-called pivot element, you cannot continue because you're supposed to divide by it. Or basically there is no multiple that you can subtract from that to kill things below it. What you do then is to switch rows. You find a non-zero element below the diagonal and exchange 2 rows. And that's and there's a definition of a matrix. So, but anyway, let's look at this a little bit more in detail on the blackboard, and then we'll implement it. So what is the method? I'm going to write it in terms of matrices, of course. Not that we might need it right now, but we might in the long run. So we say that we have a matrix A, which is an array of numbers. Typically, we use small numbers small letters corresponding to the big letter for the matrix, small letters for the actual entries, and then with subscripts. Although this is confusing, because in MATLAB you would do A parenthesis, big A parenthesis, I comma j, right? And in fact, we often use that notation on the blackboard. MATLAB has kind of infiltrated. It's such a powerful language in linear algebra. It has, people write research papers where they use MATLAB notation with colons and stuff because it's a powerful notation. Anyway, by this we just mean that we have a matrix, and the first index is always the row. So this is what it looks like, right? The first index is the row. The second index is the column. Right? And then we said this time a solution vector. So we also introduce a solution vector. And you may or may not want to put a bold or an arrow or something to indicate that it's a vector. That's, of course, just these guys. And here I give a big MATLAB warning that, you know, in linear algebra, we differ between row and column vectors. But usually, when we want to multiply matrices and vectors, we mean column vectors. In MATLAB, if you do bracket 1, 2, 3, what does it become? Hint, it does not become what you want. 1 comma, if you do commas, it puts it on the same line, right? Then you do semicolon and you get on the next line. So if you want this, you got to do 1 semicolon 2 semicolon 3. And most people don't. Actually, it's so annoying to press semicolon. So I often do 1, 2, 3 bracket, and then I transpose it. Same thing, okay? So anyway, I'm just warning you about that. And then eventually we had a b, which is the same thing. It's a bunch of numbers. Bn. And using this, you can write your whole system in a form where we augment the matrix A by the vector B, just so we can do Gaussian elimination on everything. So you're really putting all these numbers here, and often we do a little line like that, and here we put the B's. And here we put the matrix A. Right? That's what you do. Gaussian elimination, the goal of Gaussian elimination is to, I'm messing this up. Let's do that so we see it correctly. The goal of Gaussian elimination is to take this lower, the part below the diagonal, including, I wanted it to include this guy, and set to 0. That's the goal of Gaussian elimination. Without changing the solution of the system, you want to do that. Doing these elementary row operations. All right? I could do a silly example, but I'm not gonna because you kind of know how to do Gaussian elimination. So let's just start directly at creating a computer code for it. So that might be a little new for you, but by doing it by hand, you would certainly know which operations to do. But let's think about how to do it for a computer. So what are we doing? Remember the 3 operations? I can bring them up there again. Actually, the most fundamental operation is number 2. We're going to subtract multiples of one equation from another. How do we set this guy to 0? We multiply this first equation by some appropriate multiple and subtract from here, right? And we make this 0, and this is whatever it is. And then you keep on going. In fact, you use this number as the so-called pivot to 0 out all of these guys. Okay? So you take a of 1, 1. You look at a of 2, 1, 3, 1. You have a loop over here. And you try to 0 them out. So what is the structure going to be of this code? It sounds like when I'm done with that, I'm going to go over to the next one, right? And I'm going to go all the way. In fact, I'm not quite going to n. When I'm on n, I'm done. So I would say there's a big outer loop, which only goes to n minus 1. And that's, you know, we'll see. We'll see. We can verify all of this in a little while. But I claim that you need something like that. You need to be able to start at row 1 and go to n minus 1. And this I, you could give a better name, but in linear algebra, everything is I, j, k, n, m. And I is really your current pivot row. Then what? Now you're standing at the current pivot. Now we go inside this for loop, right? What are we going to do for a given I? For a given I, you want to look at the next one and the next, and the next, all the way down to the bottom, and zero them out. So why don't we do a new for loop? Sounds like a new for loop, right? And it's going to start at not I, but I plus 1, and go all the way to the bottom. And why not call it j? So there's that loop. All right, now we can start zeroing out. And now maybe it's time to start talking numbers here. What is the number we're going to multiply the first one by such that when we subtract it from here, it will make a 0? Well, it's the multiplier. It's going to be the number you want to zero out divided by the pivot element. And we'll see that later, but it's kind of straightforward. So we call that m usually. And it's going to be a of j I divided by a of I. Okay, this is a little mix of MATLAB code, but it's essentially MATLAB. No, we'll see. It's not quite MATLAB because then I need parentheses around the a's and stuff, right? So it's a what we call pseudocode. We're mixing. Pseudocode is nice. You can write whatever you want as long as it's understandable. So you mix math notation with for loops in MATLAB notation. Do you all agree that if I take this number here and subtract m times that number, I'm going to get 0 here? So that's the point. But I'm not going to do that. I'm going to take this entire equation and subtract m times that entire equation, because that's what I'm allowed to do. That's the number 2, the elementary row operation. So is this a new for loop? I just said the entire equation, right? I can't just write one equation. I could do this one. I could just write 1 to eliminate this, but that's not a point. I need to do the entire row. And you need to think a little bit about the indices here. And I'll describe where this comes from. But you need another loop. And it's going to go all the way to the end. And you can think about where it's going to start. But the truth is, I'll make a zoom in a little bit to see. No, let me do that already now. So halfway through, the typical case here, you're going to be standing somewhere where you have all these. We don't touch the pivot elements. But you put zeros everywhere below, right? But now we're standing at, let's say, I, pivot element equals 3, and we have not started yet. Then it looks like this, right? So this is what the matrix looked like after 2 steps of I have been performed. And I drew this just so we can see a little bit what the general case is going to be. All right? So by the way, here is a lot of non-zeros, right? So they're not zero in any way. I'm just not drawing them because they're not that interesting. Now, then I'm going through these guys. So a typical j would be here, right? Actually, let's put zeros here. Sorry about that. I should have planned this better. You've done a little bit. You've started going on this column, I3. But now you're at j here, and you want to kill it up. So how many numbers here in this matrix do you need to loop over in this when you're going to subtract that multiple from the equation? The key here is that you already have zeros before I. But you got to keep on going, of course, all the way to the full equation. So I claim that you start at I and go to m. You could even argue that you don't have to do I because you know it's going to become a 0. But let's do this. And what is the operation? A of jk. So now we're going to have a k that is running along here, right? Doing this operation. So j comma k should be what it was before minus the multiple times not the pivot element, but the corresponding element in the pivot row, right? So in this row here. So it's going to be the same thing, but row I. A, row I, column k. That's it. This is the entire Gaussian elimination. We'll do B as well. So it's very short, right? But there are some things that I'm sure even I would, you got to think about these things to get it right. But it's really describing in computer code in an algorithm what you know how to do by hand. Let's do the B as well. Remember, there's a B over here. And when you subtract that row from this row times m or whatever, you got to do the same thing with that B. And is that a for loop? No, because B is just a vector, right? So it comes out here. There's no inner for loop needed for that. So this one really says that B of j equals B of j minus the multiple times B of I. End. End. Isn't that a beautiful code? So think about it. It's kind of nice to know what's going on. I'll code it up in a typical MATLAB code. I actually do have one, so let's Gauss elim no pivot. I have a function on the web page that is doing this already, but it's going to be something we don't know yet. So let's start just to show how easy it is to code this up by creating a new file. And what are inputs and outputs for a typical function solving AX equals B? Inputs are A and B, right? Output is X. Fine. No pivot of A comma B. That should be easy. In a computer code, I throw around n's all the time, right? Coming in here, n is not known. If you know other languages, typically there would be an input argument n, but in MATLAB you don't need that, right? Because you look at the matrix and you see what size it is. So for example, the number of rows of A is n, right? Of course, a good code, I remember I told you the difference between our codes and real production codes. Now we should check that it's a square matrix, that B has the same number. You need all these checks. We're going to ignore them. But I'm just saying this is kind of what you want. Now we can almost copy this as it is, just to see what happens. You want I from 1 to n minus 1. You want a j from I plus 1 to n. You want a multiplier, which is A. And now, of course, there's a MATLAB thing I mentioned. This is really, MATLAB doesn't know about little a, and even less does it know about subscripts, right? The notation for this in MATLAB is big. It's the matrix A indexed by j comma I. And by the way, you know, my linear algebra is nice with MATLAB because here we really do start everything at 1 and go to n. So the zero-based issues we had before, MATLAB is very natural for linear algebra. In fact, you know what the math stands for, right? It's not mathematics. MATLAB is the matrix laboratory. Anyway, that's that multiple that we're going to multiply equation I by. And now we need another for loop to actually do it. And then you do A of j comma k. I'm just copying that thing there with this new notation. This should be enough, right? Let's do the B as well. B of j equals B of j minus m times B of I. That's how easy it is to implement a whole Gaussian elimination. To see that it works, why don't we just, every time we take away a number, we look at the matrix and pause. So this is a so-called debugging technique, which is a critical skill to have. And it's a, let's do it, yeah. Thank you very much. And I got it right there, good, thank you. All right, so you see why I'm doing this? This is not a functionality. You don't want to hand this into your GSI. Well, they don't run your codes anyway. But in the grad course, we have them submit codes, and the GSIs are not happy when they print a million of matrices and stuff, because it slows down and it makes it hard to see the actual answers. But I'm going to do it now so I can study it. So how do you test it? You create a matrix, random, 4 by 4. That's large enough for us. And you need a right-hand side that is random 4 by 1, right? And why don't we do format compact here and make it a little bit bigger. All right, so if you want a true solution, let's call it x0, you can cheat and use, I mean, that's a nice thing of teaching linear algebra, that the true answer is always available. You've been using backslash before. It's what MATLAB does to solve linear systems. But we're going to do it ourselves. So we're going to do Gauss, lim, no pivot of A comma B. And of course, we could run it, and hopefully it will just return. Actually, it's not going to solve for x, because I'm not done. You know what this MATLAB will say if you run it at the end of this function? X, there is no x. I don't talk about x, and yet it's claiming to return an x. It will give an error, because I'm not done. But let's do this anyway to see that it works. I did one step, and as you see, indeed, I zeroed out that guy. This, I should have printed A from the beginning. I haven't touched this row. I just zeroed out that guy, right? Now, what did I do here? If you look at it, the only number that changed was this, right? So now I have this k running all the way to n, and it's doing something. It's not zeroing out. That's not how the method works. The only zero was this because we chose the pivot to be exactly the zero there, right? Then we do the other two, and now we've updated this entire row. Then we go to the next j, and of course the first one of those will actually zero out, just like before. But then it will just update the rest of the row. These are the operations you would do by hand. Now we're done with an entire I, right? I1. And I goes to 2. And you can confirm that now, of course, we start at 2 plus 1, 3. Row number 3 is the first row we're going to start manipulating. All right, so you can get those indices out from there. But we still have to go all the way to n to modify the row. And now we're done with I2. And of course, the last one is easy, but it has to do 2 steps. Now we're done, and it's going to give us an error because we didn't do x. So that's the procedure. All right, so let's do x. It's called back substitution, and you know what it's about. It means that you've taken it to a form where back substitution. You're taking it to a form that looks like this, and you have a b as before, and it's a upper triangular matrix. We'll define these terms later, but I think it's pretty clear what I mean by an upper triangular matrix. How does back substitution work? It says that, hey, there are a lot of zeros here. This, remember, you got to know your matrix vector multiplication. A times, this matrix times x means this number times the last x, right, xn, is equal to bn. So really, I can now tell you what the last number in your x solution vector is. It's really just that divided by that, right? Then you go here, and it's not so easy because there are 2 of them, but you know this guy, xn. So you multiply this number by the xn you just computed, subtract from there, and divide by that, etc. In a code, I'm going to do it like this. Turns out to be convenient to actually start. This is a coding way. Maybe it's confusing to write it, but I'm going to just start by setting x equals b. But anyway, I'm going to have to go. So I need a loop. Can you see where the outermost loop is going to do? What's the first structure I'm going to do? I just said I start here, right? So really, it sounds like I'm going to have a row index I that starts down here, right? So I is equal to n here. And it got to go all the way down to 1, actually, because I need to solve all the numbers. So you can convince yourself that you need an I going from n downwards to 1. OK? Now, if it's the first place, let me write it down here. It's really just xi is equal to xi divided by aii. OK? What am I talking about here? Well, remember, I called that right-hand side vector b. And as I said, if you want this first one here, you just divide it by the number on the diagonal, which is ai. Right? So this works the first time. But for the other ones, you have to do the subtraction. So you're going to go up here. You have to subtract out that guy, right? And then you have another for loop. So this is going to be for j. And you can convince yourself again that this is going to not include the pivot, but all the other ones. And it's going to tell you to modify your x by subtracting out an aij times the x you computed before. All right? So I've computed an xn, for example. Then, of course, you have a number a of I comma n that needs to multiply by that xn and subtract it from the right-hand side. That's what back substitution is. I know that's not even, that's why I'm emphasizing this, that I know you know the method by hand, and turning it into computer code needs some thinking. So that's good. Let me write it while you think about it. So x is equal to b, n in steps downwards to 1, I plus 1 to n, I is I times x of j, and x of I. That's it. If I didn't mess it up, this should now, and now of course I don't want to see this again. Let's just run it. and now it gave us an x. And of course, you cheat by looking at that number you computed before, and you see they look pretty similar. Look similar, might not be, but why not subtract them? Well, they're actually surprisingly different, but there are some reasons for that. But anyway, we did it right. It wouldn't have been that close if we messed something up. So this is how the method works. I have this code on the web, so you can, or you can start from this simpler. It gets messier, a little other chunk on the web. But I just encourage you to just understand these steps. It's kind of just logical. It's really just computer programming more than linear algebra. But it's, of course, implementing an algorithm from linear algebra. Apart from that, I think you know the process very well. We didn't do row exchanges. We come to that later. Now I want to talk about operation counts, OK? You can count things. Well, I'll do it, so you don't have to worry about ups there. A natural question. Let's go back to the map. We'll do this one, too. But let's go back to this guy. So here's a new one for you. I talked a lot about efficiency and speed and stuff, but usually most of our analysis has been about accuracy. So you might want to ask, is this going to compute the right answer? And that's a different story. But for ODEs and everything, we say, are we getting the right answer? Convergence, et cetera, right? But for linear algebra, a key issue that is always also part of the analysis is how long will it take? OK? And we kind of done it with ODEs. I say that the smaller h is, the longer it takes, right? But here you really want to know, just as one simple little check, just looking at this method. Suppose I solve, I'm not going to use my, well, let's use my code. Suppose I take a 100 by 100 matrix. N is equal to 100. A equal to n of n. And have you seen tick-tock in MATLAB? Tick sets the timer, and tock, it checks it. So no pivot. This measures the time for doing that. And now here comes the question. What will the time be this now? Sorry. What? 8 times, good. So these are the questions people want to answer, how it scales, right? And it's 8 because I doubled the size of the matrix, but it's not clear at all yet exactly what this is. But everything here goes kind of between 1 or diagonal I to n. Turns out that this scales cubically, okay? And that's a number we want to derive. We're going to do it. So you can derive that the time scale scales cubically with n, and hopefully this time, now it doesn't look like 8, and there are some reasons for that. I can double run this to see that, oops, sorry. It goes down a little bit. You know, measuring time is difficult. If you do n 100, and run it a few times, well, I guess the lowest one of those are good, right? And then you do 200. And then you do these a number of times. So 0.22 divided by 0.054 is just a factor of 4. These are computer issues. It's something that UCS people you know as a cache. I have to make it bigger to make it seem. To make it show. Let's do 1,000 and do A \b using MATLABs. Even bigger. Oops. You see, I should write this script, shouldn't I? Anyway, now we have a good number here. Let's double this one. OK, so I went from 2,000 to 4,000, and the time went from 0.62 to 4.2, which is a little less than 8 again. But I could measure it more carefully. It's not a convincing demo. But the reason for this is computers are very iffy. There's something called cache. They grab a chunk of memory, and it's really expensive. But when they have it, it's really fast. So sometimes so doing one operation here is not the same. But the point is, you want to see it does scale right when you go further. You want to know approximately how expensive this is. In particular, based on this, it's kind of scary. Cubic growth is very fast. I mean, you might be impressed that I solved a 4,000 by 4,000 matrix in this time on my laptop. But how long will it take to solve, if this is true the cubic, to solve 40? So then you would say 40,000 can't be that hard. Well, it's 1,000 times harder, right? So it's going to be basically 4,000 seconds or more than an hour, if it fits in my computer, which is another issue. 40,000 times 40,000 number is a big number. And you know what a byte is? Remember our on our first lectures, we talked about IEEE. Remember that our IEEE, our numbers are actually 64 bits. That's 8 bytes. If you want to figure out if it fits in your computer, you got to multiply by 8 bytes. Okay? And you probably want to divide by something like 1 gigabyte to get it in the units of gigabytes. I don't have this much memory in my computer. So I cannot even create a matrix that is 40,000 by 40,000 here. And if I try to solve it, you can, of course, buy a computer with that memory easily. I'm just saying cubic is scary. Multiply by another factor of 10, you would think 400,000 would be something manageable, right? Well, you need a supercomputer for that. Even if I could do it here, it would take 1,000 hours. And of course, the memory, that turns out to scale quadratically, so it would be pretty bad. Anyway, and then you might wonder, didn't I talk about solving linear systems with million degrees of freedom? That's because you try to, this is the dense system, you try to take advantage of zeros and stuff, but that's for later. Anyway, I'm just motivating why I want to count what's called an operation count here. Let me give you the end result. You can actually derive that this algorithm that I just wrote here is making this many multiplications and division. For historical reasons, people combine these. Of course, there are 4 operations. We are dividing. We don't care about integer operations. Of course, in the computer, there's a j that starts at I plus 1. That's not an operation. And then you add 1 every time, right? That's done so efficiently in a computer, so it's an integer operation. We don't worry. We count floating point operations. They are expensive. And the first thing we do is a division here, right? And then we do a multiplication there and a subtraction. And I guess these as well, and that's it. Right? So combining these together, you can get these counts out of it. And of course, it's the leading term that will likely be the most important. How can we get these numbers out? So let's look at the techniques for doing that. And it's a little bit, it's just combinatorics, just counting. How can you get, for example, the first ones out? First of all, you might want to need some formulas. Have you seen the formulas here on top? You seen this, right? You know the story about Gauss when he was 5 years old, and his teacher punished everybody by saying, add all the numbers from 1 to 100. And they were all working for an hour, and then it took him a minute or so. Because 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. So if you think about it, it's really 101 times 50, right? That's it. That's the formula. Anyway, you can extend that to j squared when we're going to need it. All right? So how do we go about counting? Let's do the easy one, divisions. How many divisions are you doing in this method? So this is easy because it's really just one division on this row, right? This row is doing one division. So the only question is how many times does the computer run this row? Well, not that easy. It's certainly going to do this n minus 1 times. N is a given number. But then the difficult part is that there's an I there, right? If there was not an I, this would be easy. Just multiply those, right? And there would be easy situations. But this is a little difficult. It's like a triangular character. But you can certainly write it like this. You have a sum where I goes from 1 to n minus 1. That's this for loop. And each of those, you have actually n minus I of these. So I claim it's really just this. Times 1. As in one division here, right? So again, your n minus 1 times, from I equals 1 to n minus 1. You're adding up, but the thing you're adding up, the number of things you add up here changes with I. But that's fine. You make it a function of I. And if you think about it, going from I plus 1 to n means that you're going n minus I steps. And that's the number of times this line will be executed. So times 1 gives you the number of divisions. So that's the key. You write expressions of that form. And now you have to solve it, but you can use that using that there. In fact, sum from I equals 1 to n minus 1 of n is trivial, right? It's n times n minus 1. The difficult one is the I. But that's when you use the formula up there. Just confusing because there it goes to m and we go to n minus 1. So I guess it ends up being minus n of n minus 1 half. But basically that formula gives you how to sum up something of the form of I, right? And this is just to happen. All right, let's do the other one. Multiplication is harder. Multiplications. All right, there's only one multiplication, and it's here, right? And you see why it's harder? Because, well, okay, fine, there's one down here. We should do it. I don't think I do it. No, I just ignore that. Yeah. For A. You can do that, but this is the expensive part. So what's difficult here is that every time you did one division, you're making a lot of multiplications, namely n minus I plus 1, I guess. If you start at I and go to n, the number of times you will go here is n minus 1 plus 1. But it ends up being just an expression like before. So it's going to be sum from I goes from 1 to n minus 1. And the number of multiplications is going to be, well, the same as here, n minus I of those. But for each of those, you're doing n minus I plus 1. So you've got to multiply those. And it's messy, but this is the expression. In fact, teaching 10b now with combinatorics, this is one of the problems we're doing. And I'm sure if you took Math 55, they might have done something like this as well, where it just, we want to count things in combinatorics. Whatever you can count, whether it's, balls in an urn or something, right? But counting the number of times computer codes are executed, it's just combinatorial tricks. But in this case, it's either just, there are actually various fancy tricks to count these, but let's just do the algebraic way. All right, how do we simplify this? I'm sure you can be smart, but I'm not going to be smart. I'm just going to multiply everything together and then do them one by one. So if you go and multiply together, you get an n square, and you get a minus ni, and you get a plus n. Then you get a minus ni, and then you get a plus I square, and you get a minus I. Look at all these terms. What's easy and what's not? N square is trivial. Sum from I1 to n minus 1 times n squared is really just n squared times n minus 1. You're adding up constants, okay? And that's the same with, there's another one, n here, right? So if you don't mind, I'm going to take out the constants. Well, let me group them first. So this one I identify as easy. And then I have one. Here we have things that depend on I. You see those? It's minus 2ni and minus 1i. So I guess that would be 2n plus 1, and I put the minus there. And there's an I. Remember, n's are not hard. They're just constants. And then finally, we have one of these horrible I squares, which is really just not multiplied by anything. All right? I think it ended up being that way. You mean here?
No. The first term you then squared minus n.
Because it's plus n. There we go. Thank you. Yeah, I have that here. All right, you see what I'm doing? And now it's trivial. Not trivial, but it's just algebra. So this one is, let's simplify to n plus 1 times n minus 1, right? It's just a constant times n minus 1. The next one is the first formula. So it's going to be minus 2n plus 1. And then you have one of these i's, just like before. It's going to be an n minus 1 halves. And for this one, we need the last formula, which says, unfortunately, it's going all the way to m, so you got to subtract 1 from all of those m's, which means that you get, instead of m plus 1 and m, you get m and m minus 1, right? For n. And then there's a 2m minus 1, which means you need plus 1. You need to subtract 2. It turns it into 2n minus 1 instead of plus 1, divided by 6. All right. And then I got tired of this and used the computer. But now it's just algebra, right? Basically, you get your n cubed divided by 3 plus lower order terms coming out of it. So that's how you go about that. See if it matches what I have. So I don't know if this included the b or not, but certainly you have the 1/3 of n cubed that I got. Then there is an n term that is 1/3 that does not quite match what they got, but they added it with the divisions and possibly this one. I'm not sure. So we can see how this is from the book. But certainly just adding up one. As I said, there are 4 of these, right? This is divisions, that's multiplication. You got to do subtractions as well, and possibly decide whether you want to include this or not. But this is the general idea. Now, in the book, they were doing, I don't know why they're doing, usually we're just looking for the leading order term, the n cube here. But you could write down a full expression for it, of course. Okay, so that's a general technique. That's kind of the worst that will happen, worst scenario, that you get I squares. But it can be a little tricky to identify. You can do the same thing with this method. How do you think this method scales? So the doubling the n here should really just make this 4 times, because there are 2 formulas. It's a quadratic cost, basically, right? But to get the details, you have to say you have a sum from 1 to n. Of course, the sum doesn't care if you start from the end or not, right? So you have a sum from 1 to n of n minus 1 multiplications. Same with subtractions, and possibly this line for divisions. Doing that, you get, in this case, this is easier. Is there a 1? There's a 1 division. They single out 1 division. Yeah, we can see exactly. I don't know exactly where they did it for, but this is how you add these guys up. Total operation counts end up being these. It's often referred to, it's a well-known, so the cubic thing is absolutely the first one to know. Gaussian elimination on a dense matrix scales cubically. It puts limits on what you can and cannot do. It's a fancy research field on trying to reduce it. In fact, there's something called Strassen's method that brings it down to 2.67. You can bring it down to n to the 2.376. And an outstanding question is that the best? I mean, maybe you could solve linear systems in a time that is n squared times log of n or something. Nobody knows. But the people are working in those directions. So it's kind of fundamental. If you want a constant in front of it, if you count both additions and multiplications, it's a 2/3 times n cubed. Okay? And using this, you can, in principle, measure the speed of your computer. Just roughly, of course, because of all these cache issues, etc., that I talked about. But you know what? You did, so n was 4,000. Then this expression tells me that you're doing 2/3 times n cubed. You're doing this many operations, multiplications and divisions, additions, and subtractions. So that divided by the time it took should tell you how many operations you're doing per second. And this is a number that we often report as flops, floating point operations per second. And you might be surprised that it's 10 gigaflops, given that the computer is probably just, but it combines these together. It's doing multiple operations per clock tick, basically, in the processor. So this is pretty high numbers. I mean, when people started working with these numbers were so many magnitudes less. This is just insane. But of course, we don't notice because we just run bigger and bigger problems. But anyway, this is how the operation counts go. We'll come back to operation counts later, but I just wanted to give you a little bit of a hint of how they are done. Is it confusing? It's just combinatorics. You just do it. So if you feel a little uncertain about both the steps of turning the method that you knew to computer code, as well as counting these up, there are exercises on it, but maybe not on the turning to computer code. But as I said, I posted the code here. So if you take this code and just ignore something that we'll talk about next, then it's basically the same code as I did. I'll just, for those of you who want to start with the homework on this part as well, pivoting, if you encounter a 0, what can go wrong with this method? The only thing that can go wrong is this. Okay? All the other operations are well defined. You cannot divide by 0. if you find a 0, you might remember, I'm sure you've done it in some linear algebra class somewhere, you got to find a row where this number is not 0 and just switch the rows and just pretend it never happened, right? I mean, and keep on going. So that's what you do. So if a pivot, the way this extends, and I'm going to show you a demo next time where I say that it's actually numerically, you got to do this all the time, and it's not just for zeros. Nothing will be exactly 0 numerically, but it's always trouble. So you got to make this as large as you can. So every step in a good elimination algorithm, you need to find the row with the largest I, A, and you got to flip those rows. So if you come that far, it's kind of easy. I just had a few problems on that, so you can see it. But I'll do that next time. No sense to start. So, all right, office hours now if you have questions.